we're going to be learning about related rates in calculus. I hope you enjoy. Related rates. The related rates in calculus are practical applications of implicit differentiation, where we connect how the derivative of a function over time is the rate of that function. So for example, the rate of y is equal to the derivative of y with respect to time. So if you know this, you know what we're going to do with related rates. So, for example, let's take this conical example for example. So say the height of the cone. So the height of the cone is increasing by 2 centimeters per second. So the rate, so dh by dt, so the rate is equal to 2 centimeters per second. Then we also know that the radius is twice the height, and we need to find the change for volume, so the rate of the volume. So dv is what we need to find, and we need to know that 2h is equal to r. So let's actually add in our equation. So this is just the equation of the volume of a cone. And since we're solving for volume, that's why we are using the volume formula. So let's say, for example, this right here, we don't have the rate of radius. So when we derive this, we're not going to be able to derive it fully. So what we're going to have to do is we're going to replace radius, r, with at least 2h. Because 2h is equal to r, so we're not changing the value of our example. But we are going to be able to actually find the derivative without, going through extensive processes. So here, v is equal to 1 over 3 pi 2h squared times h. And that's going to equal to 4h squared times h, which is also going to equal to 1 over 3 pi 4h cubed is equal to v. So now what we're going to do is we're going to find the derivative. So dv by dt, so the rate of the volume, that's what we're trying to find. The rate of the volume is equal to, and then let's find the derivative of this. So the derivative of this, we're going to take the exponent down, and you're going to subtract 1 from the exponent. So that's going to go to 3 times 1 over 3, so that's going to cancel. So that's going to be 4 pi h squared. And over here, we know that the radius is 6 centimeters long, and since h is going to be twice, so that's going to be 3. So h is going to be 3. But wait, we forgot. We also have to do chain rule and also have to add in the 2 centimeters over here at the end. Because when you find the derivative of h cubed, it's going to equal to 3h squared times dh by dt. So we only did this part. We forgot this one. So here we're going to have 4 pi h squared times 2. That's going to equal to 36 pi times 2, because we're going to substitute in 3. And that's going to give us a nice clean number of dv by dt. So the rate of volume change when the radius is 6 centimeters long is equal to 72 pi cm cubed, because this is volume, per second. We need to know what the unit is, because the unit is very important. So that would be the answer. 72 pi centimeters cubed per second is our radius change, so the rate of change of the volume. So now let's do a cube. Say the volume of a cube is increasing by 300 meters per cubed per minute. And over here, the volume is just going to be just 100 meters. So v is going to be equal to 100 meters cubed. dv is also going to be equal to 300 meters cubed per minute, because this is the rate. We're gonna have to find the rate of surface area and the rate of the side length. So let's think of it like this. So the cube volume is equal to S cubed. So V is equal to S cubed. Meaning, if we do the differentiation of this, we're gonna get dV by dt is equal to, and then this is gonna be 3s squared times, and then this is gonna be, this is gonna be s, so ds over dt. So over here, we don't know what the value of s is using our known values right here, so we're gonna have to find it. So let's go back to our original equation right here, v is equal to s cubed. What we're gonna do is we're gonna substitute in the actual value of v, so that's gonna be 100 is equal to s cubed. So that means s is equal to the cube root of 100, which is gonna be approximately just that. So what we're gonna do is we're gonna substitute that into here. So 3 cube root of 100 squared times ds by dt. So we're substituting the values because we know, and we know the rate of volume. The rate of volume is going to be 300 meters cubed per minute. So this is going to be 300. So we're going to cancel these two out. That's going to get us 100 here, and that's going to give us cube root of 300 power 2 times ds. So that's the rate of change of the surface area, the side length. So ds is the side length. So ds is the rate of change of the side length. So that's going to equal to 100 over 100 over this meters per minute. So now that we found ds by dt, what we can do is, when the volume of the cube is at 100 meters cubed, then the ds, so the rate of change of the side length, is 100 over root of 100 all squared. So what we're going to do is here, we're going to erase all this because we found ds by dt. So that was half of our problem finished. Now we need to find the rate of surface area. So surface area is going to be s squared times 6. So SA is equal to s squared times 6. So let me just write that down for you guys. SA for a cube is s power squared times 6. So we need to find the derivative of this. So dsa over dt is equal to 2s. So we know the s, right? 2s times ds by dt times 6. So we know that the actual s value is going to be cube root of 3. So because over here we have, again, I can run through this one more time. 100 equal to s cubed, so s is equal to cube root of 100. So 2 cube root of 100 all over, and the ds by dt is equal to cube root of that. And let's write another one like this. So we're expanding out the cube root like this, and we can cancel out the cube root right here, and this is gonna just stay the same. So that is equal to dsa by dt. So what's gonna happen is we're gonna actually write that down. So dSA by dt, okay, is equal to, okay, this is gonna be 2 over, then this is gonna be cube root of 100 times 6. So 6 times 12 is 12 cube root of 100. And that is our answer. So 12 meters squared, because this area per minute. And that's there. We just finished the problem. I'm not going to be simplifying these answers because we can just do that with a calculator. But this is in fact how we solve for the rate of the surface area and the rate of the side length. I hope you enjoyed this video. Goodbye!